Now, there is a concept in organic chemistry that has always bothered me in terms of learning the field, and this is the relative stability of the carbocations. Now, all you need to know is that a primary is less stable than a secondary, which is less stable than a tertiary. So the tertiary is going to be our most stable carbocation, secondary the second most stable, and primary the least stable. Now, the reason this bothers me is it's always come across as a circular argument. We say that the tertiary is more stable because they have more branches coming off that carbon. Well, that's kind of the definition of a tertiary carbon. So what I'm going to present to you in this video is my opinion and my understanding. However, I don't know if it's actually true regarding the relative stability of the carbocation. So what we're going to take a look at is the covalent formal charge versus the ionic oxidation states. And for me, so oxidation states represent one extreme. If we had ionic bonding in a organic compound, these would be the charges on the atoms, whereas the formal charge says, well, let's say it's 100% covalent, no electronegativity differences, what would the charge be? Now, both these pictures are wrong. The reality sits somewhere between a covalent and purely ionic compound. But for me, general observation has been that the closer those two numbers are, typically the more stable the atoms, particularly if they take opposing signs. So if your formal charge is positive and your oxidation number is negative, it implies a real disconnect in terms of the covalent and ionic pictures. So what we're going to do is we're going to represent the ionic charge here with a black marker. So if we have a CH3 group, the oxidation state is -3. For a CH, it's -1. For a CH2, it's -2. Now, the formal charge here we'll put in blue. So in all cases, our formal charge is going to be 0 for the neutral atoms. Now, let's say I put a carbocation on each of these positions. Well, to do that, I have to eliminate a hydrogen. This is how I'm going to form my carbocation. Now, when I eliminate a hydrogen, that negative charge is coming from the hydrogen. So this ends up having a 0 oxidation state, a -2 oxidation state, and a -1 oxidation state. Now, if we're going to make these into carbocations, and yeah, you'd never make this compound with 3 carbocations. I mean, good luck making it. But again, hypothetical example. This plus here is going to give all of our carbons a +1 formal charge. So for me, my understanding is this. The reason why a tertiary carbon is the most stable carbocation is that we have a 0 to +1 range for the oxidation number. So the oxidation number and the formal charge are actually relatively close. So by ionic and covalent, we get similar numbers. Here, for a secondary, we have a +1 and a -1. So this is kind of a radical difference here. And if we get here from +1 to -2, we're seeing an even bigger difference, 3 electron difference. Now the other thing is that carbon kind of sits on the more metallic side of the periodic table. So it is a non-metal. It's carbon, but it can go either way. It can take a +4 or -4, kind of straddle. It starts looking like a metalloid. So on top of that, not only are we seeing close agreement in the oxidation and covalent charges, we're also seeing more what we'd expect for carbon to act more like an electron donor. So for me, this is what explains the stability. Now, does that matter? No. If you're willing to accept that a primary is less stable than a secondary, which is less stable than a tertiary, that will work for you. And feel free just to memorize that trend. But again, for me as a student in organic chemistry, I really do want to understand why. And this is what helps me understand why. Now, all this is predicated on the assumption that you don't have a resonance structure. If you have a resonance structure that stabilizes your carbocation, all bets are off. You need to really start looking at the resonance structures. But if you just have a stable carbocation, for me, this is what explains this type of picture.